Welcome to Math 106, Chapter 2.3, where we talk about now curve sketching. So we're going to take what we've learned from Chapter 2.1 and 2.2 and now actually go ahead and create these equations. To transform these equations into a graphical sense. So it says, why do we need to even sketch? Well, first, to sketch it, it helps us understand and visualize these abstract formulas. So we can pull this information that we see from this formula or this equation, and then it helps us understand, okay, well, which information is going to do what? What does the first derivative test tell us? What information does it give? How does that transform into the equation or into the graph? And same thing with your second derivative test. Now, when it comes to your steps, we have these 4 steps. One is to compute your first and second derivatives. Then you can locate all your maxes and mins. Then you can study your concavity and locate any sort of inflection points. And then lastly, we consider all other properties such as intercepts, increasing or decreasing, and so forth. So that's what we should be able to do at the end of this section. So first, when it talks about locating your relative maxes and mins, think about a graph that either has a relative max or min, right? What is your slope at that particular point? So think about a max or a min here. First, locate your max or your min. Well, your maximum here is at your peak, and your minimum here is at your valley. Now, at that particular point, could you figure out the slope of your tangent line? We said the slope of the tangent line, if a tangent line only touches your graph once, your slope is, or you now have a horizontal line, which the slope of this horizontal line is what? Well, it's going to be equal to 0. Now, your first derivative is all about the slope of your tangent line, right? So at these particular extremas, we should have a slope that's equal to 0. In other words, your first derivative should be equal to 0. Your first derivative should be equal to 0. Whereas all else, if we're increasing, our first derivative is greater than 0. That shows us that we are increasing. And if we are decreasing, going down here, then your first derivative is less than 0. We are going, we're falling. And that's exactly what it says down here. It says at a relative extrema point, the derivative changes sign because the graph is increasing when we have our first derivative is greater than 0, so it's positive, and it decreases when it's negative or it's less than 0. Now, this can only happen when your first derivative is equal to 0. So we have some sort of a switch or a change in that direction. So it says, look at the possible relative extrema points for f of x by setting your derivative, your first derivative, equal to 0 and solving. All that is just saying is that we can set your first derivative equal to 0 and solve. So we're going to set it equal to 0 and solve for x. That's all your directions are saying. It says a number a in the domain of f such that your first derivative at that particular point a is equal to 0. This is called a critical number. So that just means this value a is your critical number. We'll label that as Cn. However, when we have your full point a and f of a, this is called a critical point, because you now actually have a full coordinate. Thus, if f has a relative extrema value at x is equal to a, then a must be a critical value. No, not every critical value extremes yields a relative extreme point. So all that is saying is that if you're looking at these points down here, or these 4 graphs down here, you'll notice that we can still have a critical value. So you can still have a critical value or a critical point, even when it's not at a max or a min. So you'll notice that these last two, we still have these horizontal lines here. and they just don't happen to be at a relative max or min. This could be a neither case. So it just says the condition of your first derivative at A is equal to 0 only tells us that the tangent line is horizontal at that A. So based on your figures above, when does the max occur? Well, looking here, we have a maximum. Well, a max occurs when we are increasing to start, and then all of a sudden we switch directions and now we go ahead and decrease. So we can just say something along the lines of the derivative you could say, instead of derivative, if you want, your first derivative changes from positive to negative. This will yield a max. Now, based on your figure, how does the minimum occur? Well, it's the other extreme. So you go from a decreasing function and then you turn it around. Then you go to increasing. So we can take that sentence over here, and all you have to do is you change it ever so slightly to say, okay, well, instead of going from positive to negative, we're now going to go from negative to positive. And I like how I'm actually color coordinating this, so I'm going to switch that around. Now, lastly, based on the last two figures, when does the extreme point not occur? So in these two figures, what do you notice? Well, in this one, our graph is going up, and then we flatten out, and then we continue back up. Or in the reverse case, we are going down, we flatten, and then we continue to go down. So for us here, in order to not have an extrema, so a max or min, we are not changing direction. You still have a critical value or a critical point. It's just not labeled as a max or min. So we could say when the first derivative does not change. So instead, maybe it goes from a positive to, again, a positive. Or from a negative to a negative. So continues from positive to positive, or from a negative to a negative. So there is no change in direction. No change in direction. So let's take a look at example 1. It says find the local max and min points of this particular function. So when we go to approach these, the first thing we said we want to do is to find these critical values, right? We want to determine these critical values where the tangent line is horizontal. Well, your tangent line is all associated about your first derivative. So your first step is to take your first derivative. So step 1, take first derivative. So if we have f of x is equal to 1/3 x to the third minus 2x squared plus 3x plus 1, we're going to take your first derivative. So we can say, okay, this is 3/3, so this just becomes x squared minus 2 times 2, that's 4, x to the first plus 3. So this is your first derivative. So first off, we want to do is take your first derivative. Step 2, we said find critical value. In doing so, all we're going to do is set your first derivative equal to 0. So we're going to take 0, and instead of having f prime of x, we're going to have 0 is equal to x squared minus 4x plus 3. Now, have we seen something like this before? Well, absolutely. We have talked about solving. This is where your factoring and solving skills come into play. So let's see if you can pause the video and factor. So factors of 3, 1, and 3, they both need to be negative in order to get to the negative 4. And then when we multiply them back together, it gets us to a positive 3. Now, when we solve, right, this is fully factored. Now we want to go ahead and solve. We can set it equal to 0. Therefore, x is equal to 1 and x is equal to 3. These are your critical values. So this is where your slope of your your slope of your tangent line is horizontal. Now, in order to go from a value into a coordinate or a point, right, we need to next find what? Well, so far we have your x value, we have 1, and now I need to know, okay, well, what is our y coordinate? Again, we have your x value of 3. We now need to figure out, again, your y coordinate. So after figuring out your critical value, we now need to go ahead and determine step 3, find the point or the y coordinate. So if we know that x is equal to 1, and again, when x is equal to 3, how do you find your point? Well, we plug it back into the original equation. So you can say f of x is equal to, and we had 1/3 x cubed minus 2x squared plus 3x plus 1. And all we're doing is we are now evaluating, instead of just x, we now get to evaluate when x is 1. So we could go ahead and just replace it. And keep in mind, you are allowed just a basic calculator here. So you plug in a 1, you get 1/3 minus 2 plus 3 plus 1. So we can say, okay, well, we have 1/3, and we can save the fraction for the end. Plus, let's see, that's 4 minus 2, so that's plus 2. And in order to get common denominator, we should get 7/3. So your point here, your critical value, your critical point is 1 7/3. Let's do it again for your 3. We're just replacing it with a 3 here. So you have 1/3 times 27 minus 6 plus, oops, and that's squared. I'm so sorry. Minus 2 times 9 plus 9 plus 1, 27/3 minus 18 plus, let's say, plus 10. And then 27 divided by 3, that's 9 minus 8. So we're equal to 1. So our point here is 3, 1. Now, in order to figure out to see if we now have a max or min. So we did all of this in order just to figure out, did we have a critical point, right? A critical value. So now if we need to determine if it's a max or a min, step 4, determine if we have a max, min, or neither. Now keep in mind what we said previously. We need to determine if it's a max or min based on if we're going from positive to negative, negative to positive, or if there's no change. So for us, when we go to test, and so far we haven't introduced the second derivative yet. So this is only one possible way. What we can do is start on a number line. We have your critical value of 1, and then again at 3. And if we're trying to figure out, okay, testing your positive and your negative slopes, right? We know that at here, your slope is equal to 0. We're horizontal. So that means that we need to just test some points in between, and you only need to do 1 for each. So what's a value that is less than 1? Well, a nice one would be maybe 0. And then again, a nice point in between 1 and 3 is perhaps 2. And the last one, a number greater than 3, is perhaps 4. So in order to determine whether or not these are going to have a max or min, or sorry, not a max or min, a critical, no, one more time. In order to determine if we're a max or min, we're looking to see your first derivative is greater than 0, less than 0. So we need to put these values into your first derivative. So test values by plugging in first derivative. So if we know that x is now equal to 0, and your first derivative we said is equal to x squared minus 4x plus 3, right? Or its factored form, x minus 3 and x minus 1. Either version of it is perfectly fine. We can go ahead and plug in a 0 into your values. So I might plug it into this particular one. F prime of 0 is 0 minus 3, 0 minus 1. So we're at negative 3 times negative 1. So a positive 3. So this is where your derivative, your first derivative, if it comes out to be a positive, we are now increasing. So we have a positive. We then flatten out here, and we're going to do it again when x is equal to 2. So same thing. When your first derivative, we're going to insert a 2, minus 3, 2 minus 1. So we're left with negative 1 times 2. So negative 2. So if it's negative, that means your first derivative is less than 0. So we are decreasing. And I shouldn't put a flatten out. We are negative. So we went from positive to negative. And then one more time. So actually, before I say that, when we go from a positive to a negative, what does that make this? Does that make it a max, a min, or neither? Well, if we went from up to flat to down, we now have a maximum. Let's try it again. One more time. When x is now equal to 4, we're left with a positive 3. So our first derivative is greater than 0. So we are back at positive. So we went from negative to flatten to then positive. Do we have a max or a min or neither? Well, here we have a min. So all in all, at our point 1 7/3, we have a maximum. And 3, 1, we have a minimum. I'm going to have you try it one more time with example 2, just based on what we have done so far. Okay, so it says find the local max and min, mins of your points given our function. So again, step 1, we need to find f prime. So if we have your function 3x minus 1 cubed, right? We are using your power rule or your chain rule, right? So we first use the power. So we go down here, 3x minus 1 squared. And then we get to take the derivative of the inside, which is just 3. So all in all, our first derivative is 9, 3x minus 1 squared. Now we get to set your first derivative equal to 0. So we have 0 is equal to 9, 3x minus 1 squared. We can divide both sides by 9. 0 is equal to 3x minus 1 squared. To undo your square, we can square root both sides. Keep in mind, every time we square root something, we need to account for both the positive and the negative half. Doesn't matter in this case because it's still 0. So you have 3x minus 1. Go ahead and solve. We can add 1 to the other side and divide by 3. So you have x is equal to 1/3. So this is our critical value. Now we need to go ahead and determine the point. So find the point by plugging in x is equal to 1/3 into your function. And the reason why we do it into your original function, because your original function is going to give us your point. So, and keep in mind, if you don't, if you need a calculator, you can certainly use one. We're going to go ahead and insert it right in. So 3, oops. We have 3 over 3, which is just 1. 1 minus 1 cubed is equal to 0. So we have the coordinate 1/3, comma 0. This is your critical point now. It started off as a critical value. Now paired with your point, we have we now have your coordinate, your full coordinate. So now last thing we need to do is to determine if we have a max, a min, or a neither. So let's go ahead and throw this point on a number line. So we said we have this 1/3 here. Now on either side, we again just get to pick a value because we're looking for, is it going to go from an increase to a decrease to an increase to increase, or decrease to decrease. So these are only 4 options available to us. So for us, a number less than 1/3, that's nice, is 0. And again, a number that's greater than 1/3, that's nice, is 1. So again, we get to determine based on your first derivative of just plugging it in. So we get to plug in a 0 into your first derivative, which we said was 9, 3x, or 3 times 0, minus 1 squared. So 9 times negative 1 squared is 9. So your first derivative here is positive. We're going up. And then again, we flatten here. And then our second test, we do the same thing. Nine times, let's see, 2 squared. 2 squared is 4, so 36. And again, it's positive. So again, this is positive. So you'll notice that if we went from a positive, so if we went up to flatten and then back up, do we have a min, max, or neither? We have a neither situation. So at our point 1/3, 0, we have neither a max nor a min. And we can see that too if I were to put my graph on here. That's this graph right here. Don't worry, I'll zoom in here in a moment. We can see our graph right here. You'll notice that we have that coordinate of 1/3, 0. So we can see that nice horizontal line of your derivative, your first derivative. And you'll notice that we are increasing. We flatten out and then we increase again. Whereas if I were to do the same, but for the one that we did previously, I'll find a good spot for it somewhere. Squish it one more time. So previously, right, you can see that we now have lots of ups and downs. Right here, we had the point 1 and what was it? 1 7/3. And then again, we had another one where it was 3, 1, where you can see a nice flat line here. We had your max and we have your min. And notice that we're going up and down, up and down. We start to go up, we change direction, we come back down, and then one more time, a switch in that direction. That is exactly what we're testing for over here. Now, we're going to introduce you to the second derivative test, which all that changes is that we're not really testing this point here or these values here. If you like this process, by all means use it. The second derivative test is just testing concavity. So it goes on to say, okay, well, if your first derivative is equal to 0 and your second derivative is less than 0, so it's negative, then we have a local maximum. Whereas if your first derivative is equal to 0, so all this is just saying is that these are critical points or a critical value, I should say. So at your critical values, if your second derivative is greater than 0, we now have a local minimum. So if you're negative here, we have a local max. We are concave down, 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 or we are positive and we're located, or we have a local minimum. We're kind of concave up. That's all that is saying. So let's have you guys try example 3 with just first to take the first derivative to find your critical values, find the critical point, and then we're going to take your derivative, your second derivative. So let's take a look here. So our first few steps remain the same. So find the first derivative of f of x. So if we have f of x is 1/4 x squared minus x plus 2. Your first derivative, we drop down the 2 and divide, and now we have x to the first minus 1. So this is our first derivative. Step 2, we now set your first derivative equal to 0. So those first few steps remain the same. Now let's go ahead and solve. We can add the 1 to the other side. Multiply both sides by 2. So x is equal to 2 is your critical value. Now let's go ahead and find the point associated with it. So step 3, find critical point. Plug in. So if we know that x is equal to 2, we're going to plug it all the way back into your original function. I'm going to erase this, put in a little bit of color. Again, you guys are able to use an equation, or not an equation, a graph or a calculator of some sort. So 2 squared is 4. So we have 4 over 4. So that's 1 minus 2 plus 2. So that's 0. I'll just say plus 0 is equal to 1. So we have a critical point at 2, 1. This is your critical point. So we got your critical point. So now if we are trying to determine your extrema based on your not first derivative test, but a second derivative test, what we end up doing is that we can plug in, step 4, we can plug in your critical value into your second derivative. Oops, so sorry. So before we plug in your critical point or critical value into your second derivative, we must take your second derivative. So first, we find the second derivative. So we take your first derivative, and now let's go ahead and find your second derivative. Now it happens to just be 1/2 for all of it, which isn't an issue because knowing your second derivative, if your second derivative is positive, we said we are concave up. It just happens to be that we're concave up over the whole duration of your function. Because if we were to think about what visual picture we can come up with this graph, is it's a parabola. We have an x squared. And this one is a concave up parabola, so we should be concave up for this whole duration. So because it is greater than 0, we should end up having a minimum. Now, we do have to do an extra step. Let's say if we didn't, if we took this step and we still had a function, then we can go ahead and test your critical points within it, which is what we're going to be doing in your next example. Now it says, can we sketch the graph? Well, if we were to sketch the graph, and then I'll actually go ahead and show you what the graph looks like. If we were to sketch the graph, we know that at some point on here, let's see, we have x is 2 and y is 1. So we have right here. We know that at this point, it's a horizontal line. And because we know that we are a minimum value, we are concave up over the whole thing, right? A concave up graph. This whole graph should look like this, where we have your minimum. And over the whole duration, we are concave up over this whole thing. And if I were to graph it for real, right here, we'd be able to see that that is in fact true, that we can see very clearly our critical value here. And we are concave up for this whole duration. And there you go. Let's have you guys try example 4. All right, so your first few are still the exact same. So number 1, find your first derivative. So if we have f of x is equal to x cubed minus 3x squared plus 5, our first derivative, 3x squared minus 6x, and that's it. Step 2, we set your first derivative equal to 0 to determine your critical values. So we can take out 3 and an x to leave behind x minus 2. So your critical values are when x is equal to 0 and when x is equal to 2. These are your critical values. Let's go ahead and find your critical points. Plug in x and x. We have 0 and 2 into your function from the very beginning, which is cubed minus 3 squared plus 5, which I'm just going to copy and paste. So we'll test it. 0, 0, 0, 2, 2, 2. So we have 5. So we have the critical point 0, 5. We then have 8 minus, let's see, 4 times 9, 36. And then plus 5. Oh, hold on. What am I doing? 12. There we go. So let's see, negative 4 plus 5. So that is a positive 1. So we have 2, 1. So these are your critical points now. Now, step 3, instead of testing, we are going to go ahead and find the second derivative. So we'll take your first derivative. Find the second derivative. So this is 6x minus 6. And because unlike last time where we could clearly see, okay, it's going to be positive for all, in our case, we do have a function, in which case we're going to go ahead and test a critical value concavity. So we know that we have 2, f is equal to 0, and f is equal to 2. And we're going to put it right into your second derivative and test it. Let's go ahead and plug it in. So we have negative 6. So on this side, your second derivative is negative. It's less than 0. It's negative, which we said if it's negative, right, we then therefore have a maximum. And on the other side, right, if we were to do it again, we get 12 minus 6. So that's a positive 6. Therefore, your second derivative is greater than 0. It came out to be a positive 6. We have the opposite. It is now a minimum. It is concave up. And you can kind of think, okay, positive, we have up, it's going up, whereas negative, it's going down, concave down. So draw the picture and then kind of associate, is it up or down? Now we're going to use this information to sketch a graph. So if we know your critical values, if I were to just draw something really quickly, we have 0, 5 here and 2, 1. Let's see. Let's say this is 1. That's 2. We said that we are concave down. So we have a maximum at our point 0, 5. So we're kind of concave down here. And then from your other side, so when x is equal to 2 or the coordinate 2, 1, we now switch to have a minimum. We're going to be concave up. So when we go ahead and connect, we'll end up swooping and then we can go off on either side. And you'll notice that here we're concave down for all of it. And we will have some sort of an inflection point because notice that there will be some point here that you switch the concavity. And then we go to concave up. So this should be something as to what your graph should look like. This being 0, 5, and this being 2, 1. And if I were to put that on here, right there. So very clear as day, you can see that this is what your graph should look like. Now we are going to determine that concavity, or not concavity, where it switches concavity, so that inflection point. So locating your inflection point. So we're under the assumption that your second derivative is continuous. An inflection point of your original function can occur only at the value of x for which your second derivative test is now equal to 0. Because the curve is concave up somewhere in your second derivative is positive, and then concave down for somewhere when your second derivative is negative. So it now has to then kind of cancel each other out. In order to do so, we just set your second derivative equal to 0 and solve for x. Note, you must check for the concavity of your nearby points to see if the concavity changes at that point. Because keep in mind, we could still have a neither situation, one where it looks like one of these, the bottom two. Because an inflection point could also be a critical value. So in example 5, right, we did all of this work here. So we're kind of tacking on in addition. So we can say maybe something over here. I'll just say continues on next page. Continues on next page. So we would say, okay, well, step 6, if we're trying to find your inflection point, we get to set your second derivative now equal to 0. We said your second derivative was equal to 6x minus 6. So we get to set it equal to 0 and solve for x. So, add the 6, divide by 6. So now we have x is equal to 1. This is the coordinate of your x coordinate of your inflection point. So we need to now determine your y coordinate. So every time we have an x, we now need to find your y coordinate. So we could say step 7, find the y coordinate by plugging it back into your original, which was f of x is equal to x cubed minus 3x squared plus 5. So we're going to go ahead and plug in the 1. One minus 3 plus 5. So let's see, that would be positive 3. So we have the inflection point 1, 3. And we can see that again on your graph here. At 1, 3, right here, we end up switching that concavity. We went from going downward facing to then upward facing after that fact. So this is where it ends up switching. Now we're gonna show you just a quick graphing cheat sheet. Feel free to pause and read. I'll just read it through once. Hopefully this gives you a good step-by-step. It says, find the first derivative of f of x, or f prime of x, to determine if you have a max, min, or neither. Find your critical value by setting f prime of x equal to 0. Find your critical point by plugging in that value back into the original. Your step 2 could be to find the second derivative to determine your concavity. Find the concavity by plugging in the critical value from the first step into your second derivative. And again, to test your concavity, we have up or down. And of course, you could do the alternating one. Instead of doing your second derivative test, you could just use the first and determine your slope, if it's positive, negative, or neither, just by testing points. Lastly, your inflection point, we set your second derivative equal to 0 to get your new x, and again, plug it back into the original and graph at the end. Now, we do have a couple extra ones. I'll show you this extra practice on a separate video, but I do want to switch gears and just talk about the connection between your graph of f of x and f prime of x. So it says, think of the derivatives of f of x as a slope function for f of x, and your y values on the graph of y equals f prime of x are the slopes of the corresponding points to the original graph. So if we have 8x minus x squared, and you have these particular slopes, right? If you have your x value, so here, whatever your x value is on your f prime, let's write this down here. So the slope of the f of x graph will become the y value of the f prime graph. And that should make sense in a roundabout way because your first derivative talks all about your slope. So your x value should remain the same. However, the slope is going to change. Your y value is going to change. So your slope, right, if we're looking here, right, your x value is the same. But now your y value is 6. So these are new coordinates. And so again, if we were to draw, or if we were to make a new coordinate, we have, let's see, 2, 4. And then 4, 0. Let's see, 6, -4. And one more, 7, -6. So if we were to therefore transfer these new coordinates onto a graphing unit, we should be seeing that we have some sort of linear trend, where again, you have these new coordinates, these coordinates here, you'll see these these y values are here. And you can see very clearly that we are trending downward. We started at a +6, then we got a little bit lower to 4, and then to 0, and then now into the negatives, and we're getting more negative. So let's have you try that once more over here. See if you can make some new coordinates with the following. Well, your new coordinate for this first one would be 0 and 18. Ooh, 18. And another one, 2, 6. And another one, 4, 2. And one more, 6, 6. So looking at your slope, right? We're increasing, then we drastically decrease, then we're decreasing a little bit more, and now we're increasing. So we should see kind of that parabola shape over here as to what is going on, right? We are starting out pretty drastic, and then we're getting less, and then 0 here, or not 0, but 2. And then we're going to continue. This most likely is not our critical value because we don't have a 0 for your slope here. And if we were to overlay them on one another, you'll see that at your critical value here, where your slope is equal to 0, that therefore, and I should maybe do this in a different color, your slope is equal to 0. This becomes 3, 0, which we there see right here at this particular function. So these become the zeros of your graph, of your first derivative.